What's up, you scholars of enlightenment? Dr. Sam Gregson, particle physicist here again. I hope you've had a brilliant week and have a fantastic weekend in store. Now, today, we're going to be discussing some fascinating new results. They're out of exoplanetary science, and they seem to suggest that we might be on the cusp of finding life elsewhere in the Milky Way. A group of exoplanetary scientists claim to have found biosignature molecules in the atmosphere of the exoplanet K2-18b. K2-18b was discovered in 2015 and sits 124 light years away from the Earth. It orbits the red dwarf star K2-18 every 33 days and has a mass 8.6 times that of the Earth, but a radius only 2.6 times as large. Its average temperature hovers just below the freezing point of water. The scientists behind these amazing claims insist that K2-18b is most likely a Hysian world with a deep global ocean. That ocean is presumably teeming with life, similar to Earth-based phytoplankton, which are pumping biosignature gases into the atmosphere. The authors of the recent studies claim that the biosignature gases DMS and DMDS could only be created by life, and hence their studies present the strongest evidence yet that life has formed elsewhere in our galaxy. These are amazing, earth-shattering, paradigm-shifting claims, but many exoplanetary scientists are very skeptical. Today, we will come to understand why. To help me dig through the latest lofty claims, I'm joined by a brilliant special guest, Dr. Ryan MacDonald. Dr. MacDonald is an astrophysicist and NASA Sagan Fellow, researching exoplanet atmospheres at the University of Michigan. His research merges observational astronomy and theoretical models with a particular emphasis on atmospheric retrieval techniques. Dr. MacDonald is currently using observations from the world's newest space observatory, GWSD, to characterize exoplanet atmospheres. Dr. MacDonald is also a passionate science communicator and produces brilliant exoplanet threads on Twitter and Blue Sky, and runs the awesome YouTube channel, Martian Colonist. So I couldn't hope for a better special guest to help me understand whether there really is life on K2-18b. So, Ryan, let's start from the very top. Tell us a little bit about the nature of this particular exoplanet K2-18b. What is this exoplanet that we see on the screen here? What is it like?
So K2-18b is unlike anything we have in our own solar system. It's a class of planet that we call a sub-Neptune. So in our own solar system, we have the 4 rocky planets, of which the Earth is the largest. And then there's a big gap in size. Yeah. You step up to Neptune, which is 4 times the size of the Earth. K2-18b is right between. It's 2.5 times the size of the Earth, and it's about 8 times the mass of the Earth. Yeah. So it's completely unprecedented. And we actually know that objects like this are actually pretty much the most common type of planet in our own galaxy. We're just unlucky to not have one to be able to study up close. So what we know for sure, we know its size, we know its mass, yeah, and hence from its density, it must be hydrogen dominated. So this is not a rocky planet. Yeah. It's perhaps more like a gas dwarf, a scaled down version of Neptune. So we know that for sure. And we also know that in amongst the hydrogen in its atmosphere, there is methane, CH4. Yeah. That was detected by the James Webb Space Telescope in some observations about 2 years ago. Yeah. But that's essentially all that we know for sure about this planet. And there are big, big debates raging about what the actual nature of the interior of the planet, what is lying beneath the hydrogen. That's really where the debate about this planet is raging at the moment.
So is that the sort of the genesis of the raging debate that we can't get hands on with this particular type of planet? So there's still a lot of kind of gray area and a lot of people trying to kind of show what model best fits the data. Is that kind of why we've got such a hot spot here on K2-18b?
Yeah, so like if you see a very large and a very massive planet and you do the modeling, you know, okay, it has to be just a scaled up version of Jupiter, like a hot Jupiter. Yeah. But planets of this mass and radius, there are multiple different ways to make a planet of that mass and radius. Yeah. You can have like a rocky surface and then hydrogen surrounding it. You could have a magma ocean with hydrogen, or, and this is where, you know, the imagination has really caught about planets like K2-18b, is if the conditions are just right, yeah, if the planet absorbs just the right amount of irradiation from its star, it reflects just about the right amount, you could have a surface of liquid water underneath the layer of hydrogen. And that is what some researchers have coined this term Hyish for, like hydrogen and ocean. But the debate on whether or not it is even physically possible to actually have a Hyish planet is raging. It's a valid solution of the equations, but a lot of things have to be absolutely right in terms of all the unknowns in these equations to make this a valid solution. Many other astronomers think it's more likely that there's no habitable liquid water surface. And obviously, if you have like a magma ocean at the bottom, there's no life on that object.
Very interesting. Okay, so that's given us some grounding on some of the claims. So let's start at a kind of high level. What do the latest papers and the latest media articles, what do they claim about this exoplanet? I think there's two main claims, isn't there? One's about the structure, as you said, this Hyish world, and one is about the kind of chemicals that we might have found in the atmosphere. What are the big claims that are being made about K2-18b?
Yeah, so the headline claim that is going around at the moment is that the James Webb Space Telescope has observed this planet K2-18b when it passes in front of its star in the mid-infrared wavelengths of light, and it has found signatures of a molecule, dimethyl sulfide, or a related molecule, dimethyl disulfide. And so here it is. You've got this is dimethyl disulfide, so 2 lots of CH3 and then 2 sulfurs. And at least on Earth, these molecules are largely produced by phytoplankton in the ocean, marine life. There are ways to produce this molecule without life. Like, it has been detected in spectra of Comet 67P. It's been seen in the interstellar medium. But there's two kind of big claims. One is the molecule is there. That's the first claim at 3 sigma significance. The second claim is then, and we think this molecule is a good signature of life. So these are the claims, and we'll of course get on to why I'm using the word claim, because most astronomers don't actually believe that this is true.
Okay, that was going to be one of my questions. And then the second claim, you talked about this Hyish world. So the idea is that there's this deep ocean that essentially is global all over the planet. Is that correct?
Yeah. So the idea is that when we observe a spectrum and we search for certain molecules, if you don't detect a molecule, that can still tell you something about the planet. And in this case, the argument is that because the molecule ammonia, NH3, has not been detected by GWSD, when you would kind of expect to see it for like a scaled down version of Neptune, that perhaps the ammonia is dissolving away into the liquid water ocean. However, ammonia can also dissolve into a magma ocean. So this one diagnostic doesn't actually tell you which of those scenarios is more likely.
Interesting. Okay, so we have this idea of this Hyish world with the idea of these biosignatures that are potentially, as you say, claimed to have been found in the atmosphere. So before we dive into the specifics of the recent work, what are your overarching feelings about these grand claims and the kind of flurry of media articles that we've seen? Because as you kind of teed up rather nicely there, a lot of people who kind of work in this field, they seem to be pretty skeptical potentially about some of these claims. What do you feel is the general consensus amongst exoplanetary experts about these claims? Obviously, I can't expect you to speak for the field, but what is your sense of how these claims have been received?
Yeah, so there's two types of claim. So there is, what does the science paper itself say? And then there is what is being reported about what the science paper says. And there's like 2 steps that are going on here. So in terms of the actual scientific paper itself, one of the things that is quite telling is that the title of the paper doesn't say detection of dimethyl sulfide or evidence of dimethyl sulfide. It actually uses the phrase new constraints on dimethyl sulfide. That's the kind of language you use if you've not seen something. And so I received a copy of the paper a couple days before it was published because some journalists asked me to comment on it. And when I looked through, my first reaction was, there actually are not any spectral features that are being strongly detected here. The data is very noisy because it's very hard to observe a planet like this in the mid-infrared. There are far fewer photons from the host star going through the atmosphere of the planet in the mid-infrared. So you can fit the data perfectly fine, just with a flat line, with no atmospheric absorption whatsoever. That is a perfectly acceptable model. So my first reaction is this a 3 sigma detection, which is what the paper says? And the answer to that, even just using the numbers reported in the paper, is no. The paper actually says that they tested 20 different molecules that could explain the spectrum, which is good. That is a really good thing that was done. And when they do that, they find that it's about 3 times more likely that either DMS or DMDS are present than that they aren't. But 3 times more likely, that's nowhere near. I mean, we wouldn't even use the word evidence for this, never mind the word detection. But then what is done is 16 of those molecules are thrown away, and the analysis is repeated just with 4 molecules: methane, carbon dioxide, and then these 2 potential biosignature molecules. And the reason this is a problem is that about half of the spectrum, so longwards of 9 microns here, you can see in this plot that DMS in cyan and DMDS in purple have stronger absorption features than methane and carbon dioxide. So if you have a model that only has these 4 molecules, you're basically forcing the model to fit the spectrum using these species. And that is where the 3 sigma number comes from. There's a couple steps along the way, like you get a Bayesian quantity that says that it's about 20 to 25 times more likely that the molecules are there. And then you plug it into a formula and magic it into an equivalent frequentist statistic. So the first thing to highlight is that this is not a 3 sigma detection. And indeed, we wouldn't even use the word detection for a result like this. You would need much better quality data with much smaller error bars to establish that. So that's the first point. Most exoplanet astronomers, and essentially everyone that I've spoken to, does not believe that this data shows that these 2 molecules are actually present. Then the second thing is, what is then announced about the findings of the paper? So unlike in 2023, when NASA put out a press release saying that methane and carbon dioxide had been detected in this planet's atmosphere, this time around, NASA was quiet. The Space Telescope Science Institute was quiet. The University of Cambridge alone put out this announcement that you see on your screens here: strongest hints of biological activity outside the solar system. And this press release takes the 3 sigma number that was quoted in the paper, which, as we've just discussed, is already problematic, and says there is a 0.3% chance that we are not seeing these molecules. When actually, from the numbers in the paper, it's more like a 28% false probability rate. So you're overstating it by a factor of 100.
They've gone straight from the kind of 3 sigma frequentist number to a percentage, but they haven't taken into account the steps that have happened in between with the modeling and the Bayesian statistics and such.
Yeah, absolutely. And so we see signals of this strength, and I even use the word like kind of signal, like very broadly here. Like, you know, I've had papers where I've seen potential signs of a molecule at stronger significance than this that has completely vanished when you get more observations or you analyze the data in a different way.
Remember, Ryan, you're talking to someone who worked at the LHC. So this was like, we called this January, right? It was like these 10 bumps that we say, oh, they've all gone by February. Fine. Okay. Move along next year. So yeah, I fully understand that. Yeah,
exactly. And the problem here is that, you know, this is being taken very literally as very strong, compelling evidence of a molecule that could indicate life. And I would say that people like to bash the media and say, oh yeah, the media is spinning things out of control. But I think this is a case where the media has largely been reporting on what the science team is saying. And in this press release, the lead author does not mince words. There are quotes like, the signal came through strong and clear. And that's not the kind of thing you'd say for something that has about a 30% chance of not being real at all.
Yeah.
And in subsequent, the quotes don't have like lots of caveats.
Yeah.
And that's really the problem. Like, I completely understand journalists kind of seeing this and then writing headlines saying that scientists think that they found life. Because that's exactly
they're
what
not
says.
They shouldn't. Well, they're not qualified to necessarily challenge the expert scientist who is saying these things.
Yeah, and the thing is, and we're seeing that is nice now is that even a week after this announcement came out, we're seeing a lot of online articles coming out that are now talking to other scientists and having headlines like other astronomers are skeptical about these findings. Because what journalists are noticing is that if they ask any other person who wasn't involved in the study, any other astronomer, almost like without exception, we're all like, there's nothing here. This is not a detection. It would be exciting if it was real, and we hope it's real. Like, we would love to find a molecule that could be a biosignature. That would motivate such a huge amount of laboratory work, theoretical work. Like, it would be an incredible discovery. But this is not it. And you only get so many chances as like professional astronomers in the exoplanet community to press the big red button and scream out aliens before people don't take the whole discipline seriously. And so, the vast majority of us exoplanet astronomers do not believe these results, and we eagerly await independent checks and reanalyses to actually see what the significance is and whether or not there could be other potential things in the atmosphere that could explain this better.
Excellent. Right. So that's a nice overview. Let's dig into some of the specifics then, so people can understand exactly what was done in these analyses and potentially where things might fall down slightly. So before we dig into those potential flaws, some of which you've already mentioned, some background housekeeping. So how do we even go about measuring the molecules that might be in an exoplanet atmosphere with a tool like GWSD? How do we actually do this?
Yeah, so there are a number of ways that we can do this, but the technique that has been used in this study, and is the most common technique we use to measure what the atmospheres these planets are made of, is called transmission spectroscopy. So you see in this graphic here that a planet passes in front of its star, and you can use that to measure how large the planet is. But if you subdivide the light from the star into very small kind of snippets of the wavelengths or the colors, you can see that at some colors of light, the planet appears ever so slightly larger because the atmosphere, the air of the planet, is absorbing that color of light. Yeah. So we are essentially observing, how does the size of the planet change with color? Yeah. And by comparing that to theoretical models and laboratory measurements that we have here on the Earth, we extract something like this. This here is a transmission spectrum of a hot giant planet, WASP-39b. It's one of the first GWSD spectra that we produced. And here, there's a very strong signal of multiple molecules. You can see by eye that the planet is larger at wavelengths with water, carbon dioxide, sulfur dioxide. So when you can see it by eye, it's clear you've got this is like a 20 sigma detection of carbon dioxide. So it's uncontroversial. But when the planets become smaller, when the planets are colder, the overall size of the atmosphere is smaller, less light goes through, and so the signal is much weaker. So you can either compensate by observing multiple transit events and combining the signal, or you have to be extra careful with how you handle the statistics to really dig into what the data is actually hiding.
And that's what we start to see. I think we've got some examples of the spectra from K2-18b. The comparison with the error bars that we see here is just night and day, right? The error bars here are completely huge compared to what we see with the WASP data.
Yeah, and so that first spectrum you're showing for K2-18b, which is from the 2023 study.
Not that one.
So this one here, yeah. So this spectrum clearly reveals that methane is there. We're seeing multiple methane absorption features with two different instruments. That is real. It's about 4 sigma or 5 sigma significance. Yeah. But intriguingly, the potential carbon dioxide feature here, which is that little bump that 3 data points are indicating, about 4.3 microns. That turned out not to actually be reliable. It was claimed to be a 3 sigma detection, but we actually went through and reanalyzed these data from scratch and found that the CO2 just vanishes, basically, depending on how you analyze the data. And equally, you'll also see DMS is written here. It was claimed to be a 1 or 2 sigma detection. That vanishes entirely when you do the reanalysis as well. And so this just illustrates that independent analyses from different teams of the same data set ultimately settles what is real, the methane is real, and what is not real, which is the DMS and carbon dioxide here.
So this data that comes down from GWST, is this the same data that everyone will get, or do you have to take some raw data from GWST and generate this spectrum? So you're talking about different groups. Do they look at the same spectrum and use different modeling, or do they have to generate these data points and generate the spectrum themselves from the raw data of the telescope?
Yeah, the data points here are an intermediate product. So the raw data from GWST is a bit of a horrible mess. It's kind of like it's like a 2D field with loads of pixels. You have cosmic ray strikes on it. The spectrum of the star is like smeared out. There are background stars and contaminants. There's a lot that you have to do in order to get to a spectrum like this. A lot of assumptions that you have to make. And you ultimately have to test them and see what is robust and what is not robust. So when we reanalyzed the raw observations, we confirmed that the methane bumps are real. But those 3 high data points that indicate carbon dioxide, we do not confirm. We do not see those. I mean, obviously, you can obtain further observations, and it may ultimately turn out that the planet does have carbon dioxide with better observations. But this observation in particular is not enough to say that CO2 or DMS are actually there. So there's a lot of steps along the way. And one thing that's worth highlighting is that the raw GWST data normally becomes publicly available to other astronomers 1 year after the observations take place. And in the case here, these observations were published about 3 months after the observations came down. But the raw data was not made available. So we actually had to wait 9 months before we could do an independent analysis, which is why there was such a long gap between these findings in 2023 and our paper went online in January of 2025 with our findings. This will not be the case with the new observations because they actually were obtained in April of last year, and I think have just become publicly available today, and that will definitely speed up the process of reanalyzing the new observations.
So just to make this clear for people, so I think we covered this a couple of years ago. So this is the spectrum from 2023, I believe.
2023.
Yeah. So at the time when these results came out, it was claimed that there was a discovery essentially of methane, of this DMS molecule, and CO2. But you have done an independent reanalysis of this, and you find that these completely disappear. So there's already a lot of tension, discussion in the community regarding what there is in this spectrum. Is that fair?
Yeah, we agree. We agree on the methane, like that's for sure real.
Okay, so let's jump into these huge claims. So the new paper, which you already teed up, which is called New Constraints on DMS and DMDS in the Atmosphere of K2-18b from GWST MIRI. The huge claim here, just make this smaller, is that we have clear detections of this dimethyl sulfide and dimethyl disulfide. What are the problems that you have with this detection? So you said that the significances are not quite as high as is being reported. So what are we seeing in the spectrum, and why can we not necessarily trust these nice underlined bold statements?
So the y-axis here is the fraction of the star's surface area that is being absorbed by the planet. So about 28% of the star's surface area is being covered by the planet. And wherever we see a bump in the spectrum, that's indicating absorption or potential absorption from a molecule in a model. So the blue curve is a model spectrum that includes dimethyl sulfide and dimethyl disulfide. And then the red points are the actual GWSD data. The problem here is that these are, the bumps that you see in the model are on the order or even smaller than the 1 sigma size of the error bars, which is the vertical extent. Yeah, they're very large error bars. And so statistically, and many astronomers immediately pointed this out on social media like Blue Sky, is that a flat line fits this data perfectly fine.
Are you just overfitting a load of noise? So you've mentioned this paper a couple of times, and I think I've definitely got it somewhere. Where did I put it? So it's I will find it eventually. So we have a flat line that actually goes through this data. So this data is so noisy that you can actually fit it with, when I can find the paper that I had. This is the Taylor paper, right?
Yes.
Where did I put it? Nope, not that one. I will find it eventually. That's your reanalysis, the new constraints. Trying to find this Taylor paper. Here we are. So the Jake Taylor paper. So if we go down in this paper, so your exoplanetary colleagues were pointing out that this data is so noisy that essentially you could fit it pretty well with a flat line, right? And the chi-squared is pretty good compared to some of the models, it seems.
Yeah, so something called the reduced chi-squared for a model that is a decent fit to the observations should be about 1. It's 1.06 here for the flat line model. So you would not be able to reject a flat line. Yeah. And yeah, you get a couple of data points that are 2 sigma outliers, but that's exactly what you would expect to see for a couple of data points. So you can't rule out a flat line. And a flat line, incidentally, physically, is what you would expect if there is not significant absorption at these wavelengths from the planetary atmosphere. Yeah. So there isn't this wavelength dependent absorption.
So what we're seeing and what people are fitting and saying are various molecules that might be in the atmosphere of this planet, it could just be noise from the telescope. Is that basically what we're saying here?
Absolutely. Ultimately, the current data is not good enough to be able to say that you've even detected the atmosphere of the planet, let alone specific molecules.
Yeah. So we'll go back to the spectrum. This is not the spectrum, the latest spectrum.
But you see that the data quality is much better in that previous spectrum because it's at shorter wavelengths where there is more signal coming in from the host star.
Yeah.
At these longer wavelengths, it's much harder to make these measurements. So the error bars here are about twice the size of the error bars from the other instruments, the ones that were reported in 2023.
So we can see in here, this is just by looking at the size of the error bars, this is not close to a 3 sigma detection as has been reported. What is the kind of base factor on this, or what is the strength of the evidence? You kind of teed up some numbers earlier.
Yeah, the base factor, so how much more probable is a model including these 2 molecules to one without them?
Yeah.
It's a little bit below 3. I think it's like 2.8 or so, using the numbers in the paper. And so that is just not a huge amount of confidence. Really, we don't talk about detections usually. And sometimes even referees say it's bad to use the word detection, even if we're talking about something that's a base factor of 150 or so. So it's very low confidence. And it's only when you knock out from the model other possible chemical species that absorb in these wavelengths, like carbon disulfide, CS2, that you force the model to include DMS and DMDS, and then you pump up the base factor to about 20 or so.
So this is the section that you were talking about, and I'm just going to find it because there seems to be a little bit of a disconnect here. There's the authors are talking about a 3 sigma detection, but they start with I believe they say it's a 2 sigma detection, and then they do this new model. So they have the original fit that we just looked at, and then can you just describe again exactly what they do with this model? How do they pump up from that 2 sigma or so that they start with to this 3 sigma? We have strong evidence that this is definitely DMS and DMDS in the spectrum.
Yeah. So if you have a model spectrum where you assume there are only 4 molecules that are present in the atmosphere besides hydrogen and helium. Methane, carbon dioxide, DMS, and DMDS.
Which feels like guiding, you're already falling into some level of confirmation bias, right, by doing this?
Yes. What we see here is from the red curve, which is methane.
Yeah.
Methane, we know the methane is there,
yeah.
and it has strong absorption between 6 microns and 9 microns.
Yeah.
So methane is a candidate to explain half of the data.
Yeah.
But then the methane absorption becomes weaker, and the CO2 absorption is kind of weak across this entire wavelength regime.
Yeah.
But there's a big rise in the absorption from dimethyl disulfide at 9 microns, and DMS has pretty strong absorption throughout the whole wavelength range.
Yeah.
So if your model can only explain strong absorption beyond 9 microns with DMDS and DMS, it has to put them in order to explain the data. So it's almost by construction that it has to put them there.
Yeah. But there could be, so you're really sort of guiding your fit to the molecules that you already are telling it are there, if that's the right way to put it, and you're falling into a level of confirmation bias there. Is that fair?
Yeah, I think that is fair. And you know what, I get, you make a theoretical prediction, you have a previous paper that shows like a hint of something, and then you want to confirm that it's real.
Yeah.
But if you really want to do that, you need better quality data. And I certainly hope that more time with this instrument, the MIRI instrument, if you could observe the planet 5 times or so, great. Then you'll get the error bar small enough that you'll really see if something is there. But this data set is not good enough to even tell you if there is an atmosphere on the planet.
So we're really going off the deep end to say that these molecules are definitely there. So the idea that we've discovered these molecules when the spectrum can be fitted with a flat line to good statistical accuracy, that seems like a bit of a stretch. And the other claim, if these molecules are there, obviously they're being produced by some kind of life, if that's what's going on. There must be an ocean there for this life to live in. So the authors suggest that K2-18b is this Hyish world that you mentioned, with a deep global ocean. So why do exoplanetary experts also question this interpretation of the GWSD data? Why are they also upset that lots of people in Cambridge are claiming that we have Hyish worlds now?
Yeah, it's because of the fine-tuning problem. So you need everything to be exactly right and interpret the available evidence in exactly the right way in order for the equations to actually produce this as a valid solution. So one particular example is that if the planet has a very low albedo, so it absorbs a lot of the light from the star, it becomes too hot to make a liquid water ocean stable at the base of this hydrogen layer. Because hydrogen also, if you have enough of it, is a greenhouse gas and also absorbs light. So you need there to be highly reflective clouds on the planet in order to allow for this ocean. And in the GWSD observations, we're not seeing any evidence that there actually are clouds on the planet, at least in the upper atmosphere that we're observing. So it's like there seems to be contradictory evidence in a number of different areas when you want to postulate the Hyish scenario. So it's like, obviously, if you think about liquid water on the Earth, for example, we know from our day-to-day experience that water can freeze pretty easily in the temperatures we're used to. You can put your water in the kettle, make a cup of tea, and then you've boiled water. It's a very narrow pressure and temperature range where you can have liquid water. So we think it's kind of more likely a priori, given it's so easy to have high temperatures underneath a hydrogen envelope, that the water is instead in a different phase of matter, like a supercritical fluid, which then can't support life. So it's really hard to have liquid water stable.
So it's very, very difficult to get this solution, which talks to it being slightly improbable. There's also, you mentioned different kind of models that fit the data, right? So this detection of CO2, but no water, carbon monoxide or NH3. So you talked about ammonia. You can solve this lack of ammonia by having this, you mentioned a magma ocean below the
Mhm.
hydrogen rather than water. So to choose one over the other when there are multiple solutions that solve or fit the data seems to be kind of jumping to the solution that you want. Is that fair?
Yeah, you need to design independent tests and make predictions for which molecules should be there or should not be there.
Yeah.
And this is a great problem for theorists to have. Like, you can build a whole career on just making predictions and seeing whether they're right or not. Ammonia was thought that it could be a good diagnostic if you didn't see it for the water ocean. But then other researchers pointed out, actually, ammonia dissolution into a magma ocean also removes it from the gas phase. So you need to keep designing kind of new tests, and eventually, hopefully, one of them will be a key discriminant of these different scenarios. And like in this graphic that you have up, for example, this scenario on the right, the miscible supercritical fluid, for another sub-Neptune we've looked at, TOI 270d, we actually found that there is so much water in the atmosphere relative to hydrogen that actually the average molecule weight in the atmosphere, it'll be about 2 times the mass of the proton if it's hydrogen dominated. But instead we see about 5 times the mass of the proton because there's a huge amount of water in the upper atmosphere. And this actually breaks the uncertainty between these scenarios and tells you that actually you have a supercritical fluid and other gases can dissolve really easily into a supercritical fluid, and that then points towards the scenario on the right. So this is an example where not just detecting molecules, but measuring how much of each molecule the atmosphere is made of, that can actually kind of break the symmetry
but this
between
comes
these
with
different scenarios.
This comes with getting enough data to be able to do that breaking, right? And while we have these low resolution spectra, these spectra with huge error bars, we can't do that breaking.
Yeah, and TOI 270d actually has inherently a stronger signal than K2-18b. So it's like you would need 4 observations or so of K2-18b to get the same error bars that we get with 1 of TOI 270. And since we're doing pretty well at figuring out what TOI 270d is like, more observations of K2-18b will only help us increase our confidence on what the planet is actually like.
So it's very, very difficult to make one of these Hyish worlds. We see other examples where we can set up tests to work out exactly what's going on, but we're not there yet, so we don't have enough data. There's also another problem, I believe, which is if this is a Hyish world with a deep ocean, why are we not detecting water in the spectrum? So I believe you mentioned when you did this reanalysis, I'll find your reanalysis, comprehensive reanalysis. Initially, Hubble detected what they thought was water on or in the atmosphere of K2-18b. This was a very over a very small wavelength range. And then when GWST followed up, that water signal went away. So if this really is a Hyish world, why are we not seeing a signal of water in the atmosphere? That naively sounds like a death knell for the Hyish world hypothesis.
Yeah. So on the Earth, if you kind of measure a parcel of gas just above the ocean, you'll see plenty of water molecules there.
Yeah.
But then as you go higher and higher, water condenses to form clouds. And then the upper atmosphere of the Earth, at the kind of heights that you go on a plane, has far less water present. So we're observing the upper atmosphere of K2-18b. So if it does have a liquid water ocean, one then has to postulate that water clouds are condensing just a little bit deeper than we're actually seeing with our observations. And essentially the water is being kind of sucked out of the gas phase to form clouds.
We're getting this kind of fine tuning, right? Where it must do this and it must do this and it must do this. But it's not necessarily killer to the Hyish world hypothesis, but it requires some.
Yeah, the non-detection of water is not a killer.
Okay. Fair enough. All right. I thought that might be killer, but that's why I ask experts and understand it better. So it's not killer that we don't see water in this spectrum for the Hyish world hypothesis. It's more about the difficulty of creating a Hyish world. Excellent. So where do we go now. So, in summary, what would you say that the latest results actually show, and what do they allow us to say about K2-18b?
In short, the latest results show that we need more observations with the Miri instrument to be able to say what is going on in the atmosphere. And if some of these bumps and wiggles turn out to actually be true, that's incredibly exciting scientifically, even if they don't turn out to be DMS or DMDS, because it could indicate some exotic sulfur chemistry in the atmosphere. But we would need to test many different molecules to actually see what could explain these. So it is a big deal getting a mid-infrared spectrum of a planet which has a temperature that would put it in the habitable zone of its host star. That is a good observational triumph. But I think it's premature to say that these observations have even detected an atmosphere. But you don't need much more time. Only a few more transits with this instrument would help to settle this question. So it's on the precipice of the signal being good enough to tell if there's an atmosphere, but it's not there yet. So more observations needed is the main takeaway.
Yeah, excellent. So just before we finish up on this, I want to touch on this idea of trying to prove that life exists elsewhere in the universe by looking for biosignatures. So we're trying to prove that life exists by showing there's kind of no other way that these molecules could exist unless life produced them. But doesn't that mean we're taking a very geocentric approach? So it seems incredibly difficult to do this, right? Because couldn't there be some, for example, some very exotic chemistry that's happening on these planets? And how can we go about, or how can we be really certain that life exists there just because we see these molecules?
Yeah, we need to understand the environment of a planet incredibly well to know that any weird molecules that we observe are not being produced by chemical processes. And as we've said earlier, the fact that we don't even know if there's a liquid water ocean or a magma ocean or a rocky surface like under all of this means we're not even at the very basic questions of what the nature of K2-18b is actually like. Because we've been arguing for, like 20 years or so about methane on Mars? Is it actually there or is it not? Is it a biosignature? There was the whole phosphine on Venus issue, which is still actively being debated as well. And we know what Mars and Venus are like. We can send spacecraft there. So you really need a good understanding of the environmental context. And then you need to detect multiple independent molecules that in that environment can't be produced significantly by life. And that is just what you need to get to the point where you even start considering that the life hypothesis is a valid hypothesis. You might then say it's a candidate planet for life, and then work on more missions or new experiments that could be designed. And I say the word experiment because we can also try then replicating the environmental conditions of that planet in the laboratory here to see whether it's possible to just naturally produce these molecules via, like, for example, like illuminating the gas with like ultraviolet light and seeing what forms. So there's a lot of work that would be required. And as you have up here, like there's a long step in the evidence chain to say confidently, we think there could be life on this planet. And the very first rung on this ladder is like, have you detected a signal that could be a biosignature? And at the moment, we're not even at that point. Most astronomers don't even believe a signal has been detected.
So step number one, do we have the statistics to say that we've definitely found one of these molecules? What we need for that is enough data. We need the features at different parts in the spectrum, and we need a certain level of sigma detection. We have to be certain about we've even seen it first. That's step number one. And we're not at the moment because the whole spectrum can be fitted with a flat line. So one not ticked. What's the second one that we need to jump through?
Well, I mean, I think there actually is a graph in this particular study that actually shows kind of some of the levels, or it's a flow chart, I think, actually. But you're like, is it there? Then it is in the environment of this object. Can we produce this molecule only with life as far as we know? Then is there a second independent line of evidence from another thing that's detected that also points towards life? And you're gradually building up like the confidence here. And it's really a couple steps down the line that you should be announcing to the public that you've got a candidate for life, not when you're not even at step one. That's the whole reason why we do these community initiatives and workshops and get different scientists to agree on when it is responsible to announce that you have a planet that could have life. And, it's a very important thing about responsibility and the credibility of the scientific community. And I think this is why there's such a backlash from the astronomy community about this new paper, because the kind of agreed upon framework that most astronomers are following is just being completely ignored.
So is this, because I can kind of understand it. This is obviously the discovery of life elsewhere in the universe would be a massive step forward. It'd be a massive thing. So is this just scientists getting ahead of themselves? I want to be the first one to have found this. I want to plant a flag here and say this is maybe, the planet where the finding will be made. Is it just people getting overexcited and getting ahead of that framework? Is that what's going on here?
Some people want it to be true. And are just really hoping that if you announce it first, then you kind of put a flag down on it. And if it turns out later to be true, then you're like, yes, we were the first to announce it. But if it doesn't turn out to be true, then you just go and find another planet and you just try it again. Yeah. Well, you think you don't lose much, but the scientific community and public trust in science does suffer via this.
Yeah. So, as you said, there's only so many times you can shout aliens before people stop listening, and we've almost done that kind of at least 1.5 times with this planet, right? Some would say 2 or more. So we have to be very careful. So, final question: what does the future look like? So you mentioned more observations of this planet to get more data, which is the first thing. Are those in the pipeline, I guess?
There is another independent team that have already observed this planet.
Okay.
And not with the MIRI instrument, but with a near-infrared instrument, NIRSPEC, and they've re-observed the planet a couple of times.
Okay.
And those observations are being worked on and publications are being prepared at the moment.
Excellent. So we are going to get some more data. Is there anything we can do on the structure side by potentially looking at these larger or Neptune-like planets in our solar system, or is this not something that would give us much of an insight?
I mean, we should absolutely do missions to orbit Uranus and Neptune, because we've only done flyby missions, and they're right there. Yeah. These ice giants in our solar system is the closest ground truth that we actually have to what some of these sub-Neptunes may actually be like.
Yeah.
So we absolutely should take the opportunity to send missions to Uranus and Neptune in the kind of like 2040s timeframe.
Yeah, I think the window opens up 2034 or something like that, and I believe
we've got to get a move on. We've really got to, because nothing's been approved yet.
There is a Uranus mission in the pipeline, I believe, but has that not been approved yet? And
there's a lot of planning and advocating for a mission, and the Uranus and Neptune planetary science communities are trying very hard to make this happen. And and it has my full support. For what it's worth, we need to get a mission to go out there.
Okay, so the Uranus missions and the Neptune missions, both of them not approved as of yet.
Yeah.
Okay, so the way we're going to get a handle on this is more data, which is going to come, potentially going to the edge of our own solar system and looking at these planets that we have, the closest versions that we have in situ. Any idea of a time frame where we might find out more information about what's going on in K2-18b? So you mentioned those other papers that are in the pipeline. Is there any idea of a time frame where the new data might be combined with what we have so far to give us more resolution on this?
Yeah, I'd be surprised if there are not more publications on new data within the next 6 months or so. And efforts will be starting on reanalysis of the new data coupled with the older data. So, there will probably be a lot more studies coming out on this planet, both old data and new, within the next year.
Did you say the new data, is that already available? I think you said this was taken last year. So is that new data that is behind the current papers, the current claims, is that now open for the rest of the community to reanalyze?
Some of the data sets are, some are not. However, usually the accepted way of doing things is to let the team that obtained the data have the first stab at publishing it before other people touch it.
Sure. So how long would you expect that will be before other people get to have a crack at this?
Well, I mean, I know conversations now that are happening about when we can download like this new MIRI data, analyzing it with old. So a lot of work is like kicking into gear right as we speak. But for, detailed analyses that go through peer review, it always takes time on the scale of months to actually do this. So it'll take time to do it right.
Yeah.
But probably for the most detailed studies, you're probably looking at 6 months.
Okay. So in 6 months, I'll come and knock on your door again, and we'll see where we're at. Ryan, thank you so much for going through that with us. It's obviously been a massive story over the last couple of weeks, and it seems like we all just need to calm down and wait for some additional data before we start screaming that we found aliens on K2-18b. Is that fair?
Absolutely.
Good stuff. Right. It's been a pleasure talking to you, buddy, as ever. I gather you're flying over to the UK soon. Take up a role at St Andrews.
Well, on Monday I'm flying to somewhere else in the US. I'm going to be collaborating with some people there for 2 weeks, and after that I'm flying over to Edinburgh. So around the middle of May is when I'll be coming over to the UK.
Superb. It'd be good to have you over here. Thank you so much again for taking the time to explain this to us, and hopefully the next time we get more information on this, we can get back together and chat again, buddy.
Thank you. I look forward to it.
It's always a pleasure. Take care.
Take care.
Bye now.
Bye.
I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.